Hi, my name is Kate Walsh, and I'm going to be sharing with you today my project, an investigation of task-induced modulation of visual cortex object representations, which sounds like a lot. We'll unpack it as we go along, but in other words, you can think of this as using neural networks to unpack the similarity of neural and behavioral representational spaces. So, the capacity for the brain to hold really complex object representations that include both visual and conceptual and personal details about your relation and memories with an object is actually a really, really complicated cognitive task that we take for granted. This ability to just have a representation, for example, for a light bulb. But having this dimension is really important, right? Because it allows us to access different parts of a representation when we need to. Let's take, for example, with this flashlight and light bulb. We know that these belong to the same object category. They share the same function, but you can see that they don't have a lot of visual overlap. And the ability to make that distinction can be valuable to us depending on the task. You can think differentially, maybe, though, about something like a crab and a lobster, which share a lot of both some conceptual and visual overlap. They're both crustaceans, but they're also both have legs and they're both reddish orange. So the ability for the brain to access these different representations when we need to is a really, really complex cognitive task that I am breaking down today. So, our overarching question here is how are specific object representations flexibly represented and accessed depending on how we intend to use that representation? More specifically, if we intend to use that information when judging, in this case, visual or conceptual similarity of different objects. We're really asking here which areas of the brain are providing the signals that are used when we are discriminating objects between categories, for example, depending on their visual or conceptual features. And we should expect, in theory, that the brain signals used in discriminating visual features should be separate or at least a little bit different from those used in discrimination of conceptual features. Where do we get into the neural networks of this? When we're judging representational similarity between this neural and behavioral data, here what we're doing is we're going to train neural networks on the neural similarities of the representations of these objects in our image set. And we're going to use those neural networks trained on the neural similarities to predict image labels for the behavioral data. Once we get a peek at what those neural and behavioral data look like, this should make a little bit more sense. But that is it for quick background. Okay, so the behavioral data that we're going to use for testing in this model comes from a previous study from my lab in which participants were asked how visually similar were two pictures or how conceptually similar two pictures were. They did this for 60 images and they did it for all possible pairs of images within those 60. So I saw that hippo with all 59 other animals that were in my image set, and I judged how visually similar that is to every 59 other animal and also how conceptually similar that hippo is to all the other animals, so that we can create an entire representational similarity space, which I'll show you in a sec. So from those behavioral judgments, we can create these representational similarity spaces, which tell us how similar all of these items are to each other. For example, you can see here, this is for all of the animals we have, and this is when they're doing visual judgments. And then you can see separately here, this is how the space looks different when they're doing conceptual judgments. And note from this point on in the presentation, just because of the field standard and how I talk about this project, I'm going to be calling this semantic rather than conceptual. But you can see actually for animals, these two spaces are really similar, and we'll get into that a little bit later. Okay, so for the neural data here, what we do is for those same images that participants saw in the behavioral task for all of those 60, it's actually 60 animate images and 60 inanimate, where animate is like animals and inanimate is things like tools. Um, so for those same, it ends up being 120 images, 60 per image category. Participants view those images one at a time in an MRI. And what every time they see an image, it's presented with a question. That question is either about their conceptual features, like this question here: is this item a tool? Is about the conceptual features of this flashlight. But I could also ask, for example, a visual question like, is this flashlight or is this item yellow? Um, and once I do that a bunch of times for every image, I end up with four presentations of each image. Twice it's presented with a semantic question, and twice it's presented with a visual question. And that allows me to get basically these patterns of activation, or these little squares that you're seeing here of activity in these brain regions. You can think of these as the representations for those objects in those brain regions under these different task conditions. Okay, these are the three guiding research questions for analysis. Just so you know, as an observer, I'm going to use the same neural network architecture to answer all of these questions. And what's going to change is the training data, validation data, and testing data. So I'm going to suggest you pause the video just for a sec right here and read these questions, and I will walk you through everything else. Okay, so this is the architecture of the artificial neural network that's used to answer all of these questions. You can see that it's actually a pretty simple architecture when it comes down to it. I only have 12 participants worth of data for a variety of reasons. And so with such a low amount of data, I didn't want to do something like a recurrent neural network that was just going to get super overfit to my limited amount of data. So I have a pretty simple architecture with some dense layers. It uses TAN-H as the activation because the values for correlations in this data set are from -1 to 1. And it also includes some dropout layers just to also work at that preventing of overfitting to the test data. And then the output layer uses softmax for activation. There are 60 possible image labels within an image category to predict. And so that is how many, that is the size of the final prediction. And then we do predictions from there. Also, just going to suggest you pause this and come back to it as needed when I'm going through the data. All right, so our first question asks, when trained on the neural dissimilarity values, can the models be used to predict images based on their behavioral dissimilarity in general? This is like a proof of concept. Ideally, this should work. So when the model is trained on the neural data, it is able to predict image labels for the behavioral data well above chance. The average accuracy ends up being 0.4, where chance accuracy 1 out of 60 is 0.02, more or less. In general, prediction of inanimate behavioral image labels is better than animate. And in both image categories, prediction of visual behavior is better than semantic behavior. Our second question asks if the models trained on visual neural data are better at predicting visual behavior compared to semantic behavior, and vice versa, if trained on semantic neural are better at predicting semantic behavior. Contrary to what you might think initially, the model does equally well for both animate and inanimate objects in visual behavior, no matter what the training data was. And you can see that for semantic behavior in both conditions, accuracy is better when trained on the visual neural data. And finally, I was interested in how well data from one of my regions of interest in the brain was able to predict data in another region of interest. I have reason to believe that these representations should be linked to each other. And in agreement with that, I find that when trained on this early visual cortex ROI, um, the model is able to perform above chance in the prediction of the late visual cortex representation data in both the animate and inanimate conditions. So what does this all mean from a technical standpoint? Well, the areas that I am looking at in the brain are really this early visual cortex information, so low-level visual information. These are the brain regions that we're looking at with these data, so it kind of makes sense. You could think about why activity in these regions is more related to visual behavioral on average compared to conceptual or semantic behavior. Right. So at this point, I'm almost certain you are thinking, so what? I just babbled on a bunch about why it matters when we think about if a flashlight is yellow. But right, the ability for us to understand how an object is represented and how we can access different parts of those representations depending on our situation has really interesting implications for our memory of those objects, how we put together memories of objects to build memories of scenes, and consequently how impacting those representations in memory disorders like Alzheimer's has really critical implications for how we interact with the world. Thanks for sticking around. I know this was super technical and probably not that interesting, especially from a modeling standpoint, but it's actually helpful for my research. So I am not mad about how this turned out. Thanks so much for sticking around.